Okay. Good afternoon, everyone. I will speak about mid-thickness studies of the stress intensity factor in the bulk of bainitc steel. First of all, I would like to thank my colleagues, Javier Vázquez Peralta, he's a PhD student, Thomas Puslav at ESRF in Grenoble, and my colleagues Chris Simpson and Phil Withers in Manchester University. So the aim of this work has been to characterize practical fields for fatigue and this can be done by linear elastic through the stress intensity factor or non-linear parameters like the J integral, crack tip opening displacement or crack tip opening angle. And this is, we've seen today and yesterday a few examples of characterization, such type of characterization with full field techniques. The initial work was done with full field, with strain gauging, and then with the developing of multi-point of a deterministic method, they found out that strain gauges was a bit painful for characterization of crack tip fields. So instead of that, they started using other full field techniques like caustics, Moiré interferometry, photoelasticity, speckle interferometry, thermoelastic stress analysis that give us like a whole full field of information, and this information can come in terms of displacement, strain, some type of stress or some of stress invariant. But the problem is that we get all this information in the surface. If we have a thin specimen or thin structure, then this is fine. But when we have a thick specimen, then what happens in the surface is not necessarily representative of what's going on in the inside. So for that, we need another type of technique. One that has been already spoken about here is finite element method. So provided we have fine enough meshing through the thickness, then we can get information from the thickness. And another one has been also Yannick Bouffier and some other colleagues talked about it. It will be with through X-ray diffraction or tomography, or even neutron diffraction as well. In this way, what we get is we can get, for example, with X-ray tomography, we can get simple information such as the evolution of the crack front, as in situ evolution of the crack front as we grow the crack. Or we can get all the more complicated things such as what Jean-Yves Bouffier normally presents, or interaction of a crack with fibers, longitudinal fibers in a metal matrix composite. And the other option, as I said, was to use X-ray diffraction for measuring strains. The idea here is that we can get, for example, if we have a vertical and horizontal detector, we can get crack growing, so elastic strain in the crack growing direction and elastic strain in the crack opening direction. Each of these maps, so this would be effectively a full field map of elastic strain, and then we get each of, if you see here, we've got, so these are the points, these marks are the points that we're actually measuring. Each of these points is actually the average of this small volume right in the center of the specimen that has these dimensions approximately 1.3 millimeters by 60 by 60 micron. Depending on the mode of X-ray diffraction, we can have this volume or we can have a slightly different volume. But in this work, we use energy dispersive mode, and this is what we measure. this is, we place this small volume right in the center of through the thickness. So the information that we are measuring is kind of well, in the middle of the thickness. And by doing so, we get this type of strain map. And this strain map, we can use it in a similar way as some colleagues talk about today, following the approach proposed by Sanford and Daly in 1979, the multi-point over the deterministic method that has two ingredients. The first one is, well, the idea is that we fit an elastic model to, or a math-analytical model to some experimental data, and from this fitting we get the stress intensity factor, or all the parameters. If we use Williams equations, well, we can use like a basic model like Williams equations, or with like 1, 2, as many terms as we want. We can use Muskelis-Willis approach, where we have a conformal a mapping function that we can use for, like, we can play a bit around with it to model a slightly different geometry, or we can even use a more advanced model like the CJP model that can give us like some values for stress intensities. In this work, we worked with a bainitc steel, Q1N, that has a relatively fine, small grain, and this is more or less a requirement for this type of experiment, because if we don't have a small grain, we cannot achieve like good accuracy for measuring like our field. This is the result of a previous experiment that we did in a stainless steel, and then basically this should look a bit like this, and then that here we should see like a K field. But instead of that, we see like this very very noisy curve, which, well, if we're trying to fit a like Williams type model here, then it's going to really struggle to fit. So that's the reason why we use the bainitc steel. The test was, we did it in the ESRF in Grenoble, here in France, in the beamline ID15A, with the energy dispersive mode and a diffraction angle of 5 degrees, and we used a 50 kilonewton Instrom brick. We can see here, well, this is the setup we had over here. The beam came, like the incident beam came from this down here, and then behind we've got like two detectors. One is here and the other one, I don't know if you can see, but it's behind the sample. And then from each of these detectors we measure the vertical or horizontal strength, elastic strength. The specimen that we used was a compact tension specimen with W equal 50 and thickness 3.3. We applied, well, we did the pre-cracking, we applied the delta K of 36 megapascal per meter, and when the crack length was 30 millimeter, and that's what we measure. Like that, at that point we measure the maximum load, we measure the strain, and that strain field is the one that we studied, or the one that we based all our study on. The first thing that we wanted to study is what's the influence of the area of interest, because well, for other full field techniques we have like plenty of data. We can, like, for example, for image correlation, we can just like bring the camera back a couple of inches, and then we have a bigger field of view, and then that gives us, I don't know, as many, we can increase the area of interest as much as we want, really. And we can also have like a bigger, like a more higher resolution camera, so that we can also have more like density of data points. But here, we are quite limited in time. So really, if we want to look at, like, say, for example, estimation of the stress intensity factor, we should ideally collect as few points as we want so that we can do as many like different experiments or like fatigue stages as we can. So because of that, we were interested in studying the influence of the area of interest. We've done that by looking at the influence of the radius of this area of interest, the radius, the outer radius, and the result is here. We can see that, well, of course, the bigger the area of interest is, the more number of terms in Williams equations we will need, and that is shown in this plot approximately. You can see these orange squares show the evolution for estimating with one term in Williams equation, and in black we have two terms and so on. And we can see that the minimum, so the minimum would be the best prediction by the model. We are plotting here the error against the outer radius of this area of interest. And we can see that the minimum is like around 350 microns for one term. When we use two terms, it's a bit bigger, so 450, and so on. For the maximum, when we use like 5 or 6 terms, we like the best predictions are with an area of interest of 950. You can see that, well, anyway, the estimations are like, provided we get the right area of interest, are like quite good, even for like 1, 2, 3, 4 terms. Another interesting aspect that we presented in our last conference, but with image correlation data, was the position of this area of interest. In our previous study, we did it on image correlation data, we were interested in knowing what's the best place to, like, which area of interest, or what should be the position of the area of interest compared to the crack tip. Our conclusion was that so the crack should be like 1/4 of the whole area of interest. Because this is really, it's really dependent on the full field technique. So if you use like photoelastic data or thermoelastic data, then this changes slightly. So that's why we were interested in looking at this effect here as well. So basically, it's just like having the area of interest right center at the crack tip, or shifted towards the left or towards the right. And well, in this case, because we had like a circular area of interest, well, we studied something similar to that through the angle alpha, and we found that the angle alpha 0 basically means we collect the whole circle, and then if we increase the angle, then we are collecting less data from behind the crack tip. So we can see here that the best results are really for collecting all of the data. So the data from behind the crack tip is useful for estimating the stress intensity factor. We also studied the effect of the plastic zone. Well, I need to remind here that we're actually using elastic strain. So the technique measures only the elastic part of the strain. So it's kind of ideal for measuring the stress intensity factor, because we get rid, we don't need to come up with a methodology for getting rid of the plasticity, but instead the methodology, the measuring tool itself only measures the elastic part. So we can see that if we get rid of the plastic zone, which is these solid symbols, the predictions are worse. Our interpretation of this is that we are collecting too few data. So for example, for one term, we are collecting either an area of interest of 350 microns, that would be this point, and then if we get rid of the plastic zone, we are removing another circle of 330 microns. So basically we are left with very few data, like a nanodot. And it seems that this is not, that's not enough data for having a good fitting between the model and the experimental data. And in line with that, we also studied the number of data points that are required for the fitting. And that has been studied through this phi number, which is the ratio between number of data points and number of terms in our Williams series. And we can see that, well, again, we're measuring, showing here the error against this phi, which is, well, like a measure of how many data points we need. And we can see that, provided we have, like, well, more than 40, so 40 times more data points than the number of terms, then we have like a good fitting. This is like, I guess this effect is, it depends on the quality of the experimental data. So if we have a lot of noise, then we would need more data, and if we have less noise, we will need less data. If we have like a perfectly like artificial image, for example, with if we have, I don't know, 3 terms, then with 3 points would be enough. But because normally with all experimental techniques we have some level of noise, then that's why we need this over-deterministic approach. So to conclude, I would like to say that, well, the first thing is that it is possible to measure the stress intensity factor experimentally in the bulk of engineering materials. That this, well, some people have done like something along these lines, but well, here we've done like a thorough analysis of what are the parameters and how well can we estimate the stress intensity factor. If we want to improve, we can improve the accuracy by increasing the number of terms. We can see a better fitting, but that also requires a larger area of interest, and that's like, well, depending on how much bin time you have for the experiment, you might be able or might not be able to collect as many data. But anyway, we've seen that with 3 or 4 terms is often sufficient, sometimes even less. With these data that I showed, even with 1 or 2 terms, often it's actually enough. We also saw that we should collect data both from ahead and from behind the crack tip for a better fitting, and that the size of the area of interest in general should be bigger than the plastic zone, at least for 1 term, and of course even larger for more terms. We've also seen in this experiment that excluding the plastic zone doesn't improve the fitting, and this is probably due to the data being elastic data, so it doesn't have any plasticity effect. And also found that the level of over-determination should be like, for this type of data, larger than 40. So I would like to acknowledge the people who, well, the institution that funded our work, and finally I would also like to dedicate this work to our colleague Václav, who passed away recently. Thank you very much for your attention.